Okay, so we are going to start now with properties of linear functions and models, and after linear we'll move into quadratic and then into polynomials. So we will get, a little bit more difficult as we go along, but we get to start with linear. So a linear function, as we know, has the form f of x equals mx plus b. Hopefully mx plus b form looks normal or looks, predictable for you, something you've seen before. And then the average rate of change, remember, is just the slope, yeah? So y2 minus y1 over x2 minus x1. It's also the change in y over the change in x. That's what this delta means. This is change in. Or we could use f of x and do f of x2 minus f of x1 over x2 minus x1. So we use function notation to get the y's. However you choose to do it, average rate of change is just slope, because this is linear. So we're going to use a table to determine if it's a linear function. For each of these tables, we are trying to figure out if it's linear. To be linear, then the average rate of change needs to be the same across the board. If it's not the same, then it's not linear. From negative 26 to negative 4, we've gone up 22. But from negative 4 to 2, we've only gone up 6. Those are not equal, so non-linear. This other one, though, from negative 4 to negative 3.5, we've gone up 0.5. From negative 3.5 to negative 3, we've gone up 0.5. From negative 3 to negative 2.5, we go up 0.5. And we do the same from negative 2.5 to negative 2. The x goes up 1 each time, right? 4, 5, 6, 7, 8. So this is linear. All right? So we're just subtracting. You could also plot those points and take a look at it if it looks linear. It's really helpful, though, if we actually have the numbers, the values here, so that we can prove that it is linear, that the average rate of change is the same across the board. There are going to be plenty of times in math that we're going to want to be able to talk about whether a function is always increasing, always decreasing, or always constant over its domain. And that will become more of a thing when you get into some of the theorems in upper levels of mathematics. But that means that we start talking about it now. And so linear functions, because they are linear, right? They are either always increasing, or always decreasing, or always constant. The slope is 0. So increasing slope means the slope is positive, decreasing means the slope is negative, and constant means 0. Slope is 0. We probably already knew that, but being able to talk about always increasing and always decreasing over the domain is an important piece as we move along. Now, we are going to do some word problems. We just did some, we're going to do some more, but these will definitely just be linear, so that makes it a little bit nicer. We're now going to suppose the company has just purchased a new machine for its manufacturing facility for $120,000. The company chooses to depreciate the machine using the straight line method over 10 years for tax purposes. This is something that you have to do for taxes. You have to figure out, okay, how much am I taking off of my taxes each year because I bought this piece of machinery that I needed. So we want to write a linear model that expresses the book value of the machine as a function of its age, right? So how much is the machine worth according to their taxes, what they're reporting, right, for depreciation every year. So we need a straight line, yeah? That's a straight line form. To do that, we need a slope and an intercept. Well, we have a point when it's 0 years old, it's worth $120,000. And they're doing this over 10 years, so at 10 years, it's worth $0. Now I have 2 points, and one of them is y-intercept, so that makes this really nice. I just have to find the slope now. y2 minus y1 over x2 minus x1. So the slope here is going to be negative 12,000 B is 120,000. So this becomes V of x negative 12,000 x plus 120,000. Okay, so V of x is this negative 12,000 x plus 120,000 is the price over a certain number of years, yeah? What's the implied domain of that function? Negative years doesn't make sense. We can't go back. We just bought it this year. And having it be worth negative dollars doesn't make sense either. If it's still a functioning machine, no one's going to force you to pay them to take it away. So the implied domain here would be at 0 to 10. We'd be going from 0 years old to 10 years old. That's the implied domain here. Now we want to graph it. All right. Oh, good. I have 10 hash marks. Okay. So 120,000, and these will go down by 12,000 each time, so that this is 60,000, and this is going to be 10, and here's 5, and it's going to go straight down. There we go. I've graphed it. See how I can make my Y scale and my X scale be different and be whatever helps me? Make sure you remember you can do that too. Now we want to know what's the book value of the machine after 4 years. So that means we want to know what's V of 4. Negative 12,000 times 4 plus 120,000 is going to be 72,000. So it's worth $72,000 after 4 years according to this method. When is the book value of the machine $64,000? Okay, 64,000 is the Y, and now I'm solving for the X. So first I have to do is subtract 120,000. Negative 56,000 equals negative 12,000 x. Divide by negative 12,000. X equals negative 4.66 repeating 7, which is really 14/3. 4 2/3 years. Oops, that's a positive. Sorry about that. So X is 4.66 repeating 7, which is really just 14/3. So 4 2/3 of a year. Okay, another word problem for us. We are told that the quantity supplied of a good, of something, is the amount of a product that a company is willing to make available for sale at a given price. So the quantity demanded of a good is the amount of a product that consumers are willing to purchase at a given price, right? You'd be more willing to purchase more iPhones or another tablet if it was cheaper, yeah? But the cheaper it is, the less likely the company is going to be willing to sell it, right? So that's how supply and demand works. Hopefully you've had some economics somewhere along the line. We're going to suppose that the quantity supplied is S and the quantity demanded D of cell phones each month are given by the following functions. P is going to be the price in dollars of the phone. So the company will supply 60p minus 900 cell phones each month, and the customers will demand negative 15p plus 28.50 per month. Okay. Equilibrium price of a product is defined as the price at which quantity supplied equals quantity demanded. So the price when S of P equals D of P. We want to find the equilibrium price of this specific cell phone and the equilibrium quantity. The equilibrium price obviously will be P. The equilibrium quantity will be either S of that P or D of that P. I guess we use D since it says the amount demanded at equilibrium price. So equilibrium just means they need to be equal. 60p minus 900 equals negative 15p plus 2850. Alright, I'm going to add 15p here, add 900 here. These will go away for us, and we're left with 75p equals 3750. Divide by 75, and we get p equals 50. So if they offer this cell phone for $50, that's going to be their equilibrium price. How many does that mean? D of 50, negative 15 times 50 plus 2850 is 2100. So they'd be willing to supply 2100 phones and they'd sell them all for $50 each. That's the very simplified equilibrium price and quantity. Now we want to know what price does the quantity supplied end up being greater than the quantity demanded, right? So at what price would we supply more than anybody would buy? So we're going to solve this inequality. S of P needs to be greater than D of P. We know the value is going to come out to 50, but do we want to be greater than 50 or less than 50? We're going to redo the math just to make sure we didn't break any inequality symbol laws. 60p minus 900 is S of P, needs to be greater than negative 15p plus 2850. Okay, so far so good. I'm allowed to add to both sides. So I'll do that. We're still at 75p greater than 3750. So P is greater than 50. So if they charge more than $50, they will supply more than the amount demanded. You might have been able to do that in your head. I sometimes can, but I don't always trust it. So I tend to do it out so that A, you can see if you weren't able to do that in your head like me, and B, so that we can prove why, right? Just saying, oh, it's true doesn't necessarily make it true. So we wanted to be able to show it. And that's it. That's all for this lesson. It's finally a short one. The next one we'll move on into some quadratics, and but for now it's just practicing with some linear stuff and really putting words to it.